Good morning, good afternoon, and good evening. This is our 8th and final workshop of 2021. We'll be hosting a final webinar in December, and I'll mention that again at the end of this session. We want to thank you all for joining us and let you know that we greatly appreciate you taking time out of your busy day to join us. I'm Tom Concolino, and I'm here with our presenters, Aya Takase and Angela Criswell. Thank you for attending Rigaku's workshop series on X-ray computed tomography and life science. This is our viewer's choice session, which is going to focus on CT data analysis using ImageJ. This session will be taking place in the lab with Aya and Angela reviewing in real time how to use ImageJ to process scans on a variety of sample types. Now, please note if you missed any of the previous webinars, you can view them on the Rigaku website, and there's links in the chat. As far as today goes, this is going to be an interactive session like our previous workshops this year. Now, we'll still be taking your questions live during the workshop, but we'll be answering them during the session, so please don't wait until the end to ask. And as usual, please submit those questions via the Q&A button at the bottom of your screen. We won't be monitoring the raised hand function, and I'll be posting relevant links in the chat window. We'll be trying to answer as many questions as we can during the workshop, and we'll respond to any unanswered questions after the session is complete. And if for whatever reason you have difficulty viewing the webinar live, please note that it is being recorded and you will be able to view this recording beginning tomorrow. And with that said, I'll turn it over to Aya and Angela.
Thanks, Tom and Angela. And thank you everyone for attending the workshop. As always, we are presenting live from our office in the Woodlands, Texas. And today's topic is viewer's choice. So we asked the viewers to vote for a favorite topic, and you chose CT data analysis using ImageJ. So that's what we're going to cover. So today we will talk about some basic operations of Fiji distribution of ImageJ at the beginning. Then we'll take a look at some CT images and do analysis on them. Then towards the end of the workshop, I would like to show you some bonus tips, which we did not cover in the last episode of ImageJ workshop. And the tips include how to change slice direction. So that's one. And we will also talk about what to do when you have to repeat the same procedures for multiple scans. What would be the easy way to do it? Then the last one is how to deal with 4D CT or time resolved CT scans. So those are the things we're going to cover today. And the tool we will use today is ImageJ. ImageJ is an open source Java program, and you can get it on either Windows, Mac OS, or Linux. And there are a couple of different distributions of ImageJ, but the one we're going to use today is Fiji. I usually recommend the Fiji distribution of ImageJ because it comes with a lot of plugins already included in one package. So once you install Fiji, you would have most of the widely used plugins. Now, today we're using Fiji distribution of ImageJ, which is an open source. So you're more than welcome to follow me and do the same analysis on your computer. But if you are going to do that, you will need Fiji already installed on your computer. And you will also need a voxel counter plugin added to it and the sample data downloaded from our website. If you don't have them yet, that's not a problem. Don't worry about it. You can just enjoy the workshop, and this is going to be recorded, as Tom said, so you can watch the recording later and try the same analysis on your computer. Okay, so with that said, let me switch the screen and let's get started. Okay. So I have ImageJ open. This is the interface. It might not look like much, but there are a lot of tools in this. And I'm going to also leave this note on listing all the shortcuts I probably will be using today. I will try to remember to mention them when I use them the first time, but I might forget. And if you wonder what did she just do to open that window, you can look at this note to see the shortcuts. Okay, so let's start with, I'm going to open one just pretty simple image. So this is a CT scan, just one cross section of a carbon fiber reinforced polymer. You see the carbon fibers as light gray, and the medium gray is the matrix, and dark gray is the void or air. So this is just one slice of CT image. Now, let's go through some of the basic operations you probably want to know how to do when you get started. The first thing is probably zoom in to see the details. You can choose this tool and left click to zoom in, or right click to zoom out. And when you zoom in a whole lot, you might want to pan too, and you can change it to this hand tool. Then you can pan through this image as well. And as far as zooming in and out goes, you can use plus or minus keys to do this. Okay, so this is zooming in and out and also panning. You probably want to adjust the brightness and the contrast as well, and that is Control-Shift-C. And you can have this brightness and the contrast dialog. You can, by the way, do that from image adjust and brightness contrast. That's the same thing. Okay. You can click auto button to get the brightness and the contrast adjusted, or if you don't like this, you can always manually adjust it too. Okay. So that's brightness and the contrast. When you have this dialog open, you will see the histogram at the top, just to get an idea of which area you're displaying by adjusting the brightness and the contrast. But if you want to see the histogram closely, you can do Control and H for histogram to open a separate dialog for histogram. And you can look at the linear and logarithmic scale graphs. You can also copy the numbers to clipboard. Maybe you can paste it to Excel spreadsheet, or you can see the numbers directly here too. So that's the histogram. Okay. Another thing you probably need sometimes, maybe you want to put this image into a report and you need to have a scale bar in it so that people can get an idea of the scale. That you can do from, so analyze, and you go to tools, then you go to scale bar. Then you will see this dialog. Now you can set the width or the length of the scale bar here. If you say 20, you can see at the right bottom, it's 20 microns. Or let's make this a little bit bigger, 50 microns. You can change the width of the line and font size. I'm going to make it bigger. And of course, you can change the color of the scale bar. You can change the location, change the font face. So you can adjust the scale bar as you like. And once you set everything, then you click OK. Now you have a scale bar. And if you have multiple slices, this scale bar goes on every single slice throughout the stack. So that's scale bar. Actually, one thing to note about scale bar is that to have a correct scale bar, the voxel size needs to be registered in the TIFF file. We're looking at a TIFF format image, and the voxel size needs to be in the header. If it's not there, you have to manually set it, and that's one of the things we will cover in this workshop later. Okay. Well, another thing you might want to do is to take some measurements. Let's say that we want to see the size of those boys. Then first, I probably want to zoom in a little bit and bring this to the center. And take this straight line tool and put a line where you want to take a measurement like this. Then you go to Analyze and Measure, or Control M. Then you will see the length calculated here. So this length is 18.91 microns. If you want to look at another one here, you can put a line here and do Control M again. The previous measurement stays in this window as far as you keep this window open. So you can take multiple measurements and have them all saved in this table. So that's taking measurements. Last one, this really doesn't have any scientific meaning, but you might, get tired of looking at a grayscale images and think that you want to change the color. And if you want to do that, you can do that too by going to image menu and look up tables. And those are the choices of color mapping. Let's pick something colorful. If you do spectrum, you can change this. This is still a single channel image. You're just changing the lookup table for different intensities. So this is another thing you can do. Okay, so these are the kind of basic operations, good to know when you're just getting started. Now, let me open the same image fresh, because this is a little bit too colorful, at least to my taste. So I'm going to open a new one, go back to the basic grayscale. We don't need this guy. Okay. So let's do some image analysis on this carbon fiber reinforced polymer CT scan. So this phase has, this sample has 3 phases. The carbon fibers, that's the highest density material, and matrix, that's in the middle, and air, those are the voids, those are the dark parts. If you want to do any quantitative analysis, for example, volume fraction analysis for the voids, or maybe fiber orientation analysis, the very first thing you have to do is to segment this image into 3 phases. So how do we go about doing that is the first polling question. So let's start the question, Angela.
All right, so I've just launched the poll so the attendees can vote. So how would you recommend that we segment this CFRP image into those 3 phases? Should I use O2 binarization, or perhaps apply smoothing and edge detection? Or do you think we should train a Weka machine learning classifier to segment? So we'll give it a few seconds to allow lots of you to vote before we share these results. We still have a few more coming in. Maybe a couple more seconds, and then I'll end this poll. Looks like we have a clear winner. I'm going to end it now, and I'm going to share the results. So the attendees have selected train Weka machine learning classifier. So I'll stop sharing and send it back to you.
Okay, well, that is the correct answer. The first 2 will get you closer to segmenting the image, but not quite. So let's try the Weka machine learning segmentation. So this is a single scan, but I'm going to use this scan to train the machine learning program, and we're going to apply it to 3D CT scan afterwards. So Weka machine learning segmentation is one of the plugins. So you go to plugins, and it's under segmentation. So it's a long way down there. There it is. And this one. You might not see exactly the same items if you're doing this with me on your computer. That's just because I have added more plugins than the original Fiji configuration. So anyway, I'm going to choose Weka segmentation trainer. And now the image is open in Weka environment. Okay, so when you use machine learning for segmentation, the way it works is you would train the machine in terms of how you would segment this image. And to do that, we have to define 3 phases. And I keep calling them phases, but in, I guess, machine learning language and also in Weka, those are called classes. So we need 3 classes. 2 classes already set, but it's probably good to change their names. So I'm going to go to settings and change their names to fiber and matrix. So now you have 2, and we need the 3rd one, that's the void. So I'm going to go to create new class to add the 3rd one. Okay, so this way, so the first choice for the polling question was binarization. And as you can probably guess from the name, binarization gives you only 2 classes. But when you use this one, you can have 3 or actually more. I think I've done this up to 7. So I know that it works up to 7 or more. So now we have 3 phases. And what you're going to do is to train this. Because I'm going to have to hand paint this image, I'm going to zoom in a little bit and take this freehand tool. And let's start with fiber. So I'm going to mark this fiber and say this is fiber. And this one is also a fiber cut at an angle. And the beauty of using machine learning is that I don't have to do this for the entire image because that would take forever. No, I don't like that because it was kind of sticking out. It doesn't need to be perfect, but you do want to do your best to get the borderline correct. So that's 3 fiber areas, and I'm going to do the same thing for the matrix. So this part is matrix. Maybe I want to zoom out and pick a different area. So that's matrix, and do the same thing for the void. And if you're trying to get the borderline like this, and if you get tired, you can do this. You don't need to walk the entire thing. So that's for the void. Okay. So I'm gonna say you need at least 2 pieces, 2 chunks painted, 3 or 4 if you have time. And I think we have enough to get started. So once you have those couple pieces painted, you can go ahead and click train classes and see what the machine comes up with. Okay. So actually, this is not too bad. This is first try. And it's not perfect, and that's okay because we're going to correct this. For example, this part is purple, but this really should be green, the matrix. What you do is you circle this and say, no, that should be green. You make corrections like this. And if you're not sure, for example, this one, I'm not sure if this is, I guess this is a combination of the void and the matrix. You can toggle the overview to see the original image. So I'm gonna say it's a little too big, but the center is void. You do this. And now there are any areas that should be green. This should be green too, right? And this too. You don't need to correct everything, but you want to pick kind of representative mistakes and correct them. Then you're going to click train again. Then the machine is going to give it a try. So this is a lot better than what we had. It's not perfect, but I think that this is close enough. Normally, you would do this couple rounds to get to the point that you're very happy with the results. Once you get to that point, you can save this classifier by going to save classifier. And I guess I'm going to just save it here. And then once you save it, you can apply this classifier to other scans, which we are going to do next. Okay. So I'm going to open another scan. And this one might look the same, but this one is 3D. It has multiple slices. So this is a 3D volume carbon fiber image. And I'm going to go back to plugins and segmentation and Weka segmentation. So now we have all the slices open in Weka environment. Then what you do to apply the classifier you just made, you're going to go to load classifier and open it. It probably will take a few seconds. Okay. So at this point, you can actually click just create result. And that classifier will be applied to the entire scan. Depending on the speed of your computer and also the file size, the creating a result part takes anywhere from a few minutes to hours. I'm not gonna run it because it's too taxing to run this calculation, then run a webinar at the same time on my computer. So I'm gonna show you the result I created before we started. So once you run it, you get something like this. So this is a 3D CT data, all labeled as 3 phases: red fiber, green matrix, and a purple void. And when you get to this point, it's actually easy to do quantitative analysis. So I'll show it an example. Minimize this. To make it easier to treat, I'm gonna switch this back to gray level and go to thresholding. And the reason why this is easy to threshold is that now you have only 3 values in histogram because it's been already segmented. So if you want to just choose fiber, you do that, just choose this one, or you can just choose the void like this and click apply just to separate this into, I'm sorry, I'm moving around the windows because they're hiding behind the zoom tools, which you don't see on your side. So if you do this, you're gonna have, in this case, just the fibers. And if you want to calculate the volume of the fibers, then you might think that, okay, I can just go to analyze and measure. And if you do that, you get the area percentage, 23%. But that's the area percentage for just this slice. If you go to a different slice and do the calculation, you get different number. So this is not volume fraction. If you want to get the volume fraction, you want to use the voxel counter. So that's in plugins. And that's B. So you go to voxel counter. And this tool will calculate the area for every single slice. As you can see the results here. Then give you the volume fraction for the entire CT scan. So to do the volume fraction calculation, you can use this plugin. Okay, so I think, yeah, that's what we wanted to do for this scan. Now, before we move on to the next image, let's see if we have any questions.
We did get a couple of questions, Aya. One of
Okay.
them, I'll let you answer. I answered already, but I'll let you mention it as well. So you have those shortcuts on your little sticky tab there.
Yes.
You just created those yourself, right? They're not, that's not something that pops up from.
No, I created it.
Right?
Yes.
Yeah.
Yes.
So okay. So maybe after you can put those shortcuts in the notes somewhere.
Okay.
People can get those really quick. I think that might be helpful in general.
You know what I can do? I have a longer list, like a big list of shortcuts, and we can put that on our website so that you can download it later.
Perfect. Okay, and we had a question come in from in the chat here, but it says it's asking, the TIFF images are obtained directly from XCT, or do you need to make the reconstruction?
Okay, good question. So I answer in 2 parts. You have to do the reconstruction no matter what the file format your analysis software takes. When you do the CT measurement, the measurement gives you just a whole bunch of 2D projections. That's not a CT scan yet until you reconstruct it. So you do have to do reconstruction. After you do the reconstruction, you will save it in the image format you want. And if you're going to use ImageJ, TIFF is probably a good format, although ImageJ supports other formats too. I think TIFF is the most widely used format for X-ray CT. It's a lossless. You're not gonna, compress and lose some information. For example, you do not want to use JPEG. If you do that, you will lose information. So, but that's how you save your reconstruction.
Okay.
I hope that
Okay.
answers the question. Yeah.
Yeah, I think that should do it. Carlos, if you have a
not,
follow-up,
put
you
follow-up
can-
questions. Yeah.
yeah, if you have a follow-up, Carlos, please go ahead and ask.
Mhm.
Okay, another couple questions here real quick. One is from Francesco. Is it possible to, I'm thinking he says kill the borders, but I think he means, frame the image to avoid particles that are not fully in the field of view? Or is that something you
Oh, I
really
see.
do?
I know that we can do that in Dragonfly. I can't think of an easy way to do it in ImageJ. If anybody knows, let us know.
What is the why would you want to get particles that are not fully in the field of view? Isn't even having the partial useful?
If
when you're
you
doing
have,
this?
for example, this guy's cut in half, right?
Yep.
And when you do, if you're doing a volume fraction, I don't think it's a problem. But if you're going to do particle size distribution as the next step, this is a problem because this is going to give you half the diameter.
Okay, very good.
It skews the results. So when you do size distribution, and if you don't have like millions of particles, it's a good practice to get rid of the edge touching particles. Yeah.
All right. Okay. Very good. So, yep. Francesco says, yeah, some commercial software has this. ImageJ does not. So if somebody wants it, they'll have to probably develop that little plugin themselves. All right. And then the final question at this step, and then we can go on to the next level, next part of the session is, can you view these voids in 3D?
You mean like a look at them in 3D?
Yes. Yes.
Yes. Let me close this guy. So we have, I selected the fibers, right? So let me do this. If you want to look at the voids, you're gonna do this. And I'm gonna just select the voids instead of fibers. I meant to select the voids. I'm not sure why I selected the fibers. Okay. Do this. Okay. So now we have just the voice, and it is 3D. We have multiple slices. Then there are a couple of different 3D viewers as plugins, but let's use Volume Viewer. This one is pretty complete. There are many functions. Okay, there you go. So you see the boys in 3D. You can see here is a really large one. There are small ones over there. And you can see cross sections in from different orientations too. You can change colors and you can change the alpha value. This one has quite a bit of flexibility to create 3D view. So you can use this. This comes with Fiji. You don't need to download it separately.
Okay. All right. So that's all the questions we have so far. So we can move on to the next section.
Good to see many questions. Please. Okay, so let's move on to something different. I don't need this guy either. Okay, so I'm gonna open this one. This is another CT scan. And if you saw Tom's post on LinkedIn, what is it, Wednesday quiz, this is the original scan. And you are looking at a cross section of particle board. There's a piece of furniture. And because of the way this was scanned, this is the surface, and you can see that the area that's close to the surface is pretty dense. You see a lot of wood pieces, not a lot of voids. But in the center area, you see very dark patches, and those are air pockets, meaning that the center area has really low packing density. And then if packing density goes higher on the other side too. And when you see something like this, it's probably interesting to analyze the packing density somewhere close to the surface for just one slice and do the same thing gradually, getting closer to the center. At the center, you probably see low packing density. But to do that, your slice needs to be parallel to the surface. The cross section, the slice we're looking at here, is perpendicular to the surface, so it's kind of inconvenient. So before I show you how to do it, Angela, let's ask the audience.
All right, so I'm going to launch the next poll. And of course, we want to know how can we make the slices parallel to the surface of the particle board? So do you think we should change the sample orientation and rerun the CT scan? Or do you think we should rotate the image 90 degrees clockwise? Or instead, should we define the surface direction and reslice this stack? So we'll give everybody a chance to get their votes in.
This
Lots
one's
of
going to
vote.
have a very clear winner.
Yeah.
Yes, it looks to have a very clear winner in this case. Maybe a couple more seconds to a couple more people. Oh, a couple more coming in. I'm going to end the poll and share the results. And so it's very clear that the audience thinks that you should define the surface direction and then reslice the stack. So I'll stop sharing and send it back to you.
Okay, and that is the correct answer. By the way, change the sample direction and rerunning the scan will work too. It's probably more work, but you can do that too. Okay, so to do the reslicing, I don't know why this guy's not giving me the straight line. I want a straight line. There you go. Okay, so I get this a straight line tool and draw a line that's, get close to the surface, parallel to the surface. Okay, this is the direction of the slice we want. So put a line like this, then go to image and draw the line, right? Okay, and where is the stacks? Did I choose the wrong one? I'm sorry. The Zoom camera view is hiding my menu. Let me move it here a little bit. Okay, there you go. Image and stacks. I was looking for it and I just couldn't find it. So it's image menu and stacks, and you go to reslice. There you go. And in this dialog, you get to choose the output spacing, and that's the thickness of the slice. And it's probably a good idea to choose something close to the voxel size. And I think the voxel size for this scan is about 29.5 microns. So let's do 30. And you type in how many slices you want. If you do 200, you go from here to here. I want to go all the way here. So we do 580, a little bit more. 90, I think that should do. Okay, then click OK. Then you can see that the ImageJ is reslicing this 3D volume, and you get this. So grab this window. Nope.
There's something in the way of your.
Yeah, actually, your face is in the way.
Oh, of course I am.
There you go.
You just turned me off.
Okay, so we have this image, and now the slice is parallel to the surface of the sample. You can see that it's very densely packed, and when you get closer to the center, you have a lot of voids, right? So now we can do the slice analysis. Let me minimize this. I'm going to duplicate this image. Okay, the entire stack, so that we have two images we can compare next to each other. Okay. I think I placed the camera in the wrong place today. That's why I'm having a hard time grabbing everybody. Okay. Let me do this. There you go. I put you to the side, Tom.
As usual.
Virtually.
Yeah.
Okay. So we have two images, the same images next to each other. Okay. Now what we want to do is to binarize one of them. So I'm going to choose this one and go to image, adjust, and threshold. Okay. And you can try different algorithms to see which one would give you a reasonable result. Now for this one, let me do the contrast adjustment. Okay. So this really dark area here too, and you have some streaks of air inside of wood pieces. We want to choose only those parts. And if you go by the default setting, I think we're over selecting the void. So I'm going to try different algorithms. For example, this one doesn't work at all. This one is about the same as the default one. And I think that this one is pretty good. So you can see that some of the small pieces that are not air are not selected, and only the air, the very dark parts are selected. So I think that this should work, the minimum error algorithm. So let's use this algorithm and separate the image into two phases. Okay, so now it's just black and white. It's either solid or air. Now it's easy to calculate the packing density. So let's start with the surface area. Okay. So do Control M, and you realize that it calculated the area, but not the area percentage. And that is because that parameter is not selected in Analyze and Set Measurements dialog. So this is where you can choose what you want to see in the results window. And what we want to do is area fraction analysis. So I'm going to check this and click OK. And let's do this again. And now you see the area 0.65%. So on the surface area, you don't have a whole lot of air and it's really well packed. But if you go a couple slices in, and it goes up to 3.1% air. And if you go a little bit deeper, 8.4%. If you go all the way to the middle, it's 17%. So you can see that the air volume percentage gradually changes as you go from the surface to the middle. Okay. So if you want to do this type of slice by slice analysis and the slice direction is not in the right direction, you can use reslicing to change it. Okay. Okay, before we go on to the next set of scans, let's see if we got more questions.
We do. We've had several come in. So
Okay.
Let's start with it's kind of two questions here. Is ImageJ works with reconstructed slices, or is the reconstruction is made with another software previously? So where are you getting your? Are you reconstructing these slices in a different software? Okay.
So depending on the CT scanner you use, you might use different reconstruction programs. But if you if you purchase a regular, commercially available CT scanner, usually the CT scanner comes with a reconstruction program, because there are a lot of things you have to tune to do the reconstruction in terms of how you did the experiment. And those parameters are specific to the machine you're using. So reconstruction software usually comes with a CT scanner, and that's probably the best choice to do the reconstruction. If you don't have one, you have the hardware, but you don't have access to reconstruction software. And that's something I believe, I can't remember the name right now, but there are open source reconstruction programs, and software packages like a Dragonfly has its own reconstruction program. VG Studio has its own as well. So you can use a third-party reconstruction program as well. But usually Scanner has a reconstruction program on it.
Okay. Okay. Several more questions. This we'll keep going here. So it was Don asks, is there a commercial version of ImageJ coming out? So for industrial CT, he had heard there might be one coming in the future. Have you heard any such murmurings.
Commercial version of ImageJ.
Yeah, or for industrial CT, let's say. So maybe it's a little more focused. But he's saying for industrial CT.
So I think there are a couple different ways to interpret this statement, meaning that software company might create something that's open source. That's, ImageJ commercial version in a way. ImageJ was originally made by NIH, and it was and still is meant to be open source. So if you make a commercial version to sell ImageJ, that I am not aware of in that discussion. But if you're thinking about just industrial, let's say metrology, dimensional analysis version of ImageJ, I am not aware of it, but I would not be surprised if somebody makes a plugin that does metrology dimensional analysis within ImageJ. That sounds like a reasonable thing to do.
Okay, so Don, if that wasn't exactly what you meant, go ahead and type in a follow-up, and we can answer that question more clearly if that's not what you were thinking of. Okay, another question was somebody who's relatively new to ImageJ is you have TIFF images of single slices and TIFF stacks, which are multiple slices. How do you save the TIFF file that it is 3D versus only one slice? Is that part of the reconstruction, or is that, how does it,
okay.
right? How do you create the single stack versus a single image, single TIFF image?
So for example, this one, let me just close this. We created this stack. It has 590 slices. So this is 3D, it's a TIFF stack. If you want to save this, you go to File and go to Save As. And if you choose TIFF under Save As, you will save this entire stack as a single TIFF file. And you can do this up to certain file size, but when you go to like a 2, 5, 10 gigabyte of file, then you cannot put everything in one TIFF file. Then you go to image sequence, and this will let you choose in which format you want to save it in, and you want to say TIFF, and you can, let's see, I can show you how this will go. Let's save this in the results, and I'm going to make a folder for this. And if you save it this way, what's going to happen in the results folder? So this is the one we just created. You will have a single slice as a single file. And you have another one like this. And you end up having 590 files in one folder. You can do it either way, depending on the file size and also depending on how you want to save it. But in a nutshell, you go to File, Save As, and choose the one that would work for you. You can save a stack with no problem.
Okay. All right. So Don came back a little more specific here. Is not a commercial version, but just a singularly focused on CT version of ImageJ. Right. So ImageJ is fairly broad in terms of what it can handle.
It's broad, and also it's at least it started as a 2D image analysis tool. So it's leaning towards 2D, I think. But more people are using it for CT, I think. So it wouldn't make sense if there was a CT oriented version of it. And if there are people for working on it, I would say that please use a GPU more if you're going to do CT image analysis. There are some plugins that will let you utilize a GPU more inside of ImageJ, but what you can do with those tools are still limited. So
okay. All right. So a couple more questions, and then we can we'll get on to the next session. So Jennifer's asking, do you continue to press Control M to get the new measurements after you slide through a slice in the resliced volume? So do you have to press Control M every time when you get to the next?
Every time, right. Okay. You go to a new slice and hit Control M and you get a result for that slice. Then you go to next slice and you hit Control M and you get another number.
Okay, okay. All right. Sarah asked, and this I'm not sure. So what's the best way to subtract different scans of the same thing made during a time series to see changes? So we may come back to this when you do your 4D CT.
It might make more sense when we look
Yeah,
at
I
the
think it's a
next
good
scan.
question. We'll cover that one later. And then Jingyi asked, for the WECA segmentation, is that included in Fiji or
Yes, it
separate
is.
download?
Yes, it
Okay.
is.
All right.
If you're already
Very-
if you're already using certain distribution of image, and if you don't have a WECA, you can just add WECA. But if you got Fiji, then WECA is already included.
Okay. All right. Okay. So that's all the questions. Sarah, we'll come back to yours when we do the 4D CT at the end
Okay.
or near the end.
All right. So let's look at the next one, which is a 4D CT scan. So I'm going to open 5 scans at a time. Well, one at a time, 5 scans. I know they all look the same, but so this scan, let's go to the middle where the sample is. Let me do this. Okay. So this is a scan at 1080 minutes mark. And this one is a scan from the same sample at 50-minute mark. The next one is 20. Let's see if people can guess what they're looking at. This is 20 minutes. And this is 10. And this is the first one. This is 0. So those are 5 scans on exactly the same sample at different time. The first one is 0 minute and 10, 20, 50, and 1080 minutes. You are looking at bread dough rising. The first one is the scan I did right after I prepared the dough and shaped it into like a small dinner roll size and did a scan. And I left the dough inside of the machine and it kept running scans all the way to next day. So that's what you're looking at, the dough changing over time. Now, what we want to do here is, so this is a 4D CT. This is a time resolved the CT scan. And it's probably convenient to put everything in one stack so that you can scroll through different cross sections. So this is Z direction. And also you want to scroll through time. So you want to create the time axis. So that's the last exercise we're going to do. But to do that, I want to make this file a little bit smaller because when you combine 5 CT scans, that can be a really big file. So I'm going to focus on this one and I want to crop it and also set the voxel size so that we can do some measurements later. Now, I have 5 scans. You know, sometimes you might have 10, 20, 30 scans to deal with. If you're going to change the voxel size and crop it, you probably want to find a good way, easy way to repeat that on 5, 10, 20, 30 scans. So that is the next polling question.
All right, so that poll question has now been launched, and we want you to pick the easiest way to repeat this procedure for all 5 of these image stacks. Do you think you should write down the procedure and make sure it's applied in the same way to all the stacks? Or do you recommend instead writing a program to execute the procedure, perhaps in Java? Or do you instead think that we should record the procedure as a macro on the first stack and then run it on the remaining stacks? So we have.
This question might have been too easy.
I think, yeah, this was a leading question, I think.
Yeah.
All right, we have more than 50% of the votes in at this point. I'll just give a couple more seconds. And wow.
No, we already have a winner with more than 50%.
We have a,
yes.
Yeah.
Oh,
so not, it wasn't quite 100%.
that's right.
Nearly
all right.
unanimous.
Not quite. All right, I'm going to end it. I'm sharing those results, and you almost unanimously the audience thinks you should record the procedure as a macro and apply it. So,
Yes.
and one vote for write it down and do it over and over again.
That's
So
a
stop
faculty member going old school.
And it's
So
back to you, Aya.
Writing it down and doing it over and over works. That's fine. Probably not the easiest way to do this. So let's make a macro. So most of you got this right. And if you know how to just type in and write a macro, go ahead and do so. But if you're not familiar with the language to do it, the easiest way to do this is to go to plugins. And I'm gonna go back all the way to the top and go to macros. And I wanna record what I'm gonna do. And just open this recorder. Then you just go about doing your business. So I wanted to crop it first. To do this, make sure that the sample is not going to go outside of this range. And the dough is going to rise. So I'm going to have a little bit slack at the top and do Control-Shift-X. So now this is cropped. Okay. And I want to change or set the voxel size for this image. You can set it's 1 centimeter. This is not set right. This image was collected at 1 pixel being equal to 144 microns or 0.144 millimeters. I'm gonna set that. Okay. Then this is the scan I want to use. So I'm gonna just go ahead and save it and replace the original. So once you do this, I didn't want to do the smoothing. So everything is recorded here, and I had one thing I didn't want, so you can just delete it like this, okay? And if you're happy with this, you can create a macro. And if you want to change the size of the cropping, you can change it here, but I'm going to keep this the same because I want everybody to be the same size. And then go to the next scan and click run. There you go. So this is easier, definitely, than writing everything down and doing the same thing over and over. There you go. And if you're going to use this macro later, you can save it and do the same thing for similar scans. But now we got 5 scans all nicely cropped and the voxel sizes is set. And we are ready to create one stack that has a time axis. Now to do that, you go to image and stacks, tools, and tools and concatenate. I always thought this was concentrate for some reason. It's concatenate. I thought concentrate doesn't really make sense for this procedure, and turns out I was the wrong one. Once you go to this concatenator, you will have the list of all the images you have open right now. And what you want to do is to choose the first image, 0 minute at the top. I probably should have closed some of them before I got to this point, but that's okay. You go to 50 and 1080, then you choose none and everything becomes black. So I have 5 scans, 0 minute, 10, 20, 50, 1080 minutes. And I'm going to combine them all to create one scan. Okay, so now you have the familiar z-axis to go through different slices. And you can stop at one slice, then this is your time axis. So you can go from 0 minute, 10, 20, 50, next day. So now you have a time axis. So this is how you can create one file that has time axis. And for CT scan, you have only grayscale 1 channel. If you do the same thing for optical microscopes, for example, then you will have probably 3 channels, and you can do the same thing. You will just have channel slider, and you have the Z and time. You will have 3 lines at the bottom, but this is how you can create one stack with time axis. Now, the last question is, what do we call this, just terminology wise in ImageJ?
All right, so time to vote one last time. Is this called a 4D stack? Is it called a hyperstack? Is it called a super stack? Or is it called a super hyper duper stack? Okay, got quite a few votes coming in. We've hit the 50% mark. Anybody else want to vote? Here we go, a few more. All right, so I'm going to end this poll. I'm going to share the results. So most of you think it's called a 4D stack, and the other results were sort of even. So I'll stop sharing and send it back to Aya to answer that question.
So I kind of agree with the 4D stack would make more sense, but I guess technically this stack can be used for something else, not just 4D, right? So ImageJ calls this go here, hyperstacks. You might have seen this in the menu. So just terminology wise, it's called a hyperstack. And I thought it's good to know the right term, because if you want to Google some sort of hyperstack operation plugin, you want to know the right name for this. So it is called hyperstack. Okay. Now, I guess we'll wrap this up and go back to Q&A. Back to the slides. So we just covered some basic operations in CT image analysis using ImageJ, and we covered 3 tips: how to reslice the images, and how to create a macro, and also how to deal with the 4D CT or hyperstacks. Now, just one thing before we go to Q&A. I don't know if you remember, but we said that we will be keeping track of which questions and how many questions you will get right throughout the season. And this was the result. So this histogram shows on points you got correct per person. And if you didn't get any of them right, you're actually in the major category, 0 or 2 points. So don't feel bad about it. But there are several people who got more than 10 points. And as one of the viewers suggested, we want to announce the winners. So Masaaki, you got 14 points. You were the single first place winner. Then we got Joe, John, Orlando, Sean, Chandra, Miles, and Chanyan. And if I didn't pronounce your name right, I'm sorry. I'll do my best. But congratulations, you got more than 10 points. And more than anything, thank you for participating for all the workshops throughout the years. And we will be contacting you individually to get your mailing address to send you a small gift. It's not an iPhone 13, but something nice. Okay, so let's take a couple more questions in the last few minutes.
All right. Yeah. So we do have just a couple of minutes here. So I'm going to go through these questions fairly quickly. So Sarah's question, this is the one about the comparing time scan data. So is there a way to subtract, right? Subtract 2 scans to view the difference? Say you have a fracture at time 0 versus time 2 hours. And it doesn't necessarily have to be an ImageJ, but is there a way to do that?
You can do image A minus image B type of calculation in ImageJ. So that's not a problem. Does that reveal the crack? Well, that's a different question, because if location of something or size of the sample changes, the simple subtraction might not do the job, but subtraction itself can be done in ImageJ.
Okay.
I think it's under analysis, if I remember it right.
All right. All right. Another one here, and I had to do a quick search to find out myself. Is there a deep learning plugin for ImageJ?
There is, right? I never used it. I haven't tried it yet. It's called Deep ImageJ. Is that right?
That's what it's called. Yes. Yep.
Okay.
Yep.
So I guess the answer is yes, but I haven't tried it yet. Maybe Angela and I will explore it and do another workshop on it.
Yeah. All right. So I put a link to the the quick reference for this, and actually I put that deep ImageJ link. I had to dig it out myself when the message came in. So those are in the chat if anybody wants to dig into themselves. Siobhan will contact you directly to answer your question after the session. Okay. So that's all the time that we do have for questions. And again, Siobhan, we'll get back to you. Muti just came in with a quick question. We'll get back to you as well. We need to wrap up for today. We'll get back to all of you directly. As I said earlier, a recording of the webinar will be available tomorrow, and an email will go out with instructions on how to view the recorded presentation. Links to the resources mentioned today will also be shared on our landing page. Also, we'll be hosting our final webinar of 2021, focusing on the preparation of life science samples on Wednesday, December the 15th at 2 p.m. Eastern, 11 a.m. Pacific time. We hope to see you then. Thank you for joining us, and we will see you again in December.